Okay, so this is about 3.10, linearization and differentials. So there's not too much new. I know I say this about a lot of sections lately, but in my opinion, this is an easy section. Um, Linearization and differentials are both just kind of, in my mind, they're just different names or different ways of thinking about tangent lines, and we've been talking about tangent lines for a long time now. Um, so yeah, it's just to recall how do we do a tangent line? It's the line whose slope is the derivative. So the tangent line through a particular point to a particular function is here it is in point slope form. And of course it goes through this point, x naught, y naught, and what is the slope? The slope is the derivative taken at the appropriate point, which is the x coordinate of this, so it's f prime of x naught. So then what is the linearization? The linearization is, it's basically, it's the exact same thing. It's just we're gonna, instead of writing y, we're gonna write L of x, and instead of writing it like this, I'm gonna move y naught over. So the y naught would come over, and that's actually this. F of x naught is the same as y naught, right? If this point is on the curve, then f of x naught is just another name for y naught. So this y naught that came over, that's the same as this. And then this is the same as this, right? Because m is the same as f prime of x naught. We said that up here. So there's nothing, I mean, I encourage you to look at this formula, and I mean, it does look a bit different from this, but I'm pointing out that it's really the same thing. So conceptually, there's not a whole lot new here. So let me talk about differentials. Differential is basically, it's like the derivative. If you remember writing, I'll make a little bubble here. If you just take this, these are just two different notations for the derivative. Sometimes we write dy over dx, and other times I write f prime of x. And in this notation, usually, like, we don't think of dy and dx as numbers. This is one symbol. We don't really think of this as a fraction. It's not like a number divided by another number. It's just a notation that means the derivative. For a differential, it's like we're kind of taking apart this fraction. We're acting like these are numbers, like dy is a number and dx is a number, and I can multiply by dx to move it over here. And if I did that, I would get this. So, and how does this make sense? This makes sense if you plug in very small numbers for dy and dx. But maybe I shouldn't talk about that too much. I'll show you in the examples what I mean. So let's do an example. We're going to use these, but I'm also going to show you one thing that they're good for. One thing that they're good for is to find an approximation. This is the square root of 9.1. So let me, first of all, I can give you like just an approximation without thinking too hard. And here's my approximation without thinking too hard. 9.1 is about 9. So square root of 9 would be 3. So this should be close-ish to 3. And it depends how close I want to be. If I'm okay with being off by a bit, then maybe it's okay to say this is close enough to 3. But we're going to do something a bit better than that. Here's what we're going to do. We're still going to use the fact that this is close to 9, and we're still going to use the fact that we know the square root of 9. But we're going to adjust. Our guess is not going to be exactly 3. We're going to adjust that guess by a bit. What we're really doing here is, here's a graph of the square root of x, And here, I mean, I know it's small, but here's x equals 9. And so we know this point. This is like the point 9, comma 3. What I'm going to do is I'm going to find the linearization, that's the red line, at this point. And then what I actually want, of course, is, maybe I should have drawn a bigger graph, but what I actually want is I would like to evaluate the function at a point that's just slightly to the right of x equals 9. Well, I want x equals 9.1. So what I'm going to do is I'm going to find the point on the linearization corresponding to x equals 9.1. That's what I'm going to do. So, yeah, of course, now I have to do it. F of x is the function that I'm dealing with, which is the square root of x, which is x to the 1/2. I know I'm going to need the derivative, so let me just find that. 1/2 x to the minus 1/2. And now let me start putting together the linearization. So, first of all, what is my x naught? For this one in the instructions, I was kind enough to tell you where to find the linearization at. They won't always tell you where to find it, but you can guess where to find it. The value 9 is just chosen to be a convenient number that's close to what we're trying to do, instead of doing the square root of 9.1. Because 9, first of all, 9's a nice whole number, and second of all, because we know the square root of 9, and that's a nice number, it makes sense to choose x equals 9. So in general, whenever you're doing this, choose the linearization, choose it at a nice number that's convenient and that's close to the number that you're really trying to do. Yeah, so like I said, we're putting together our linearization here. I'm using this formula. What's f of x naught? That would be 3, right? Because I'm just plugging 9 into this function. So f of x naught is 3. What's f prime of x naught? Well, I would plug in 9 to here, so it would be 1/2 times 9 to the negative 1/2. And what's that? How do you do negative powers? 9 to the negative 1/2 would be 1 over 9 to the 1/2. So that's 1/2 times 1/3, so I get 1/6. So, yeah. I'll have to use my space wisely here, but it should be all right. Right, so L of x, I think I'm ready to just write down L of x, would be, let's see, it's f of x naught, which is 3, plus f prime of x naught, which is 1/6, x minus x naught. Finally, what did I want? I really wanted L of 9.1. So what I get is 3 plus 1/6 times, I guess, 0.1, right? And here you can kind of see, like I said, the first guess that I made, the guess that I said, you know, without even thinking about it too hard, let's say 9.1 is close to 9, and so this should be close to 3. And then I said, our better guess is not going to be 3, it's going to be like adjusted. This is the adjustment. So here you can see the 3, and the linearization is telling us actually the square root of 9.1 should be a little bit bigger than 3, because we're doing the square root of a number that's a little bit bigger than 9. And this is not an exact answer. This is not going to be the exact square root of 9.1, but it's an approximation of how much more than 3 our answer should really be. But, yep, And as usual, I need to give a decimal for something. So what is 3 plus 0.1 over 6? This is about 3.01, and then it's like 6's repeating forever, so I'll just round it off at some point. And yeah, I don't want to write equals. This is approximately. On the homework, they'll tell you to round it off after a certain number of decimal places, so you'll know what to do. Okay. Let's see how we can use differentials to do the same thing. And maybe this will give you an idea of what differentials are good for. So we're kind of going to repeat the same work. It's going to look different, but it's going to be really fundamentally a repetition of what we already did. I'm going to consider the same function, x to the 1/2. I'm going to find its differential. So what is the differential? The differential is just the derivative times dx. So it's the derivative of this, and actually we already found the derivative of this, but it's that times dx. Now I'm going to consider a particular value of x. The value of x I'm going to consider is 9. It's the same as this one. Now I'm going to choose dx. What dx represents, it's like a small change in x. And I'm going to choose a number. The number I'm going to choose is, what is the small change that I would like to make to x? The small change I would like to make to this x is 0.1. I would like to add 0.1 to it. That's what I'm trying to do. So dx is how much I want to change x by. And I plug that in to find dy. So I get 1/2. And again, like you're probably having deja vu, we already did 9 to the negative 1/2. And in fact, we did this up here. So, you know, this is giving me 1/6 times 0.1, which if I want an approximation is 0.01667. In fact, again, we saw this before. That was here. And this is how much I described. This is what I described as how much we need to adjust our initial guess by. If our initial guess is 3, this tells us how much to adjust it. So, right. When x equals 9, y equals 3. Again, this is going back to the same old fact that square root of 9 is 3. When x is 9.1, y is going to be, it's going to be the old value of y plus dy, which is telling me how much to adjust it. So of course we get the same answer again, and it's kind of two different ways, but as I pointed out, these ways are fundamentally the same. And right, maybe this illustrates what differentials are good for. It's good for approximating small changes in x and small changes in y. Okay, so let me just do a couple more examples, and really these are just kind of excuses for me to have some fun taking some derivatives and practicing things like the chain rule and the product rule. So we're going to find the linearization of a particular function at a particular point. We have a formula for it. Whoops. Yeah, so first of all, what do we need for this formula? I need f of x naught and f prime of x naught. X naught is pi, so let me start by finding f of pi. Luckily, sine of pi is 0, so that's just 1. Now I need f prime of pi. So first, I'll take the derivative. So how do I take the derivative of this? I would say I have the chain rule. The outside function is the exponential part, so the derivative of e to the x is e to the x. So the derivative of e to the this is going to be e to the this times the derivative of the inside. And I've done this a few times where I'm kind of, I don't even want to worry about what that derivative is right now. I just want to do one thing at a time. Of course, the very next thing I have to do is worry about what that derivative is. But this is a product rule. So derivative of x is 1 times sine x plus x times derivative of sine x, which is cosine x. So there we go. What I really wanted was f prime of pi, so that's going to be, okay, if I'm smart, I can remember that when I plugged pi in here, this was e to the 0, which was 1. So that's what happens there. What happens inside here? Okay, sine of 0, or sine of pi is still 0. Cosine of pi is negative 1, right? Because pi is the same as 180 degrees, so pi is pointing straight to the left. So I would be looking at this point. The cosine is the x-coordinate. The x-coordinate of this is negative 1. Yeah, so this is 1 times negative pi, so I get negative pi. Okay, so then we're good. We just have to assemble our answer by putting it in this formula. So L of x, it's f of x naught, which is 1, plus f prime of x naught, which is negative pi, so actually I'll write minus pi, times x minus x naught. So that's the linearization. Okay, one more, where we find a differential. Let's find dy if y is this. Of course, maybe I can start writing. dy, really, again, this example is just kind of a sneaky way of me sneaking in some practice taking derivatives. dy is just the derivative times dx. So all of the work for this problem is just finding the derivative. All I have to do is find the derivative and then write dx there. So I'm about to find the derivative. Let me put this in a form that is friendly for calculus. First of all, remember how we interpret a power on top of here. It's like tangent in parentheses squared. So I'm going to use square brackets. So right, this is what's happening with the squared. Also, this x to the square root of x, I would prefer this way. Okay, so this is now, it's the same thing. I haven't done any calculus yet. I just rewrote this so that it would be friendlier when I take the derivative. Now, let me take the derivative. So I see the chain rule, and the outside function is easy for me to tell now that I wrote it this way. The outside function is squaring. So to take the derivative, I get 2. So the power comes down, and then I would have the same thing to the 1 power, because I reduce the power. And now I would multiply by the derivative of the inside. And maybe I'll try to do, I'll actually start to do this. So what is the derivative of tangent of this? Well, I'm still doing the chain rule. So the first thing I'm going to do is the derivative of tangent. The derivative of tangent is secant squared. And then I would need to multiply by the derivative of that inside. So actually, I might end up doing this derivative all in one step at this rate. So what's the derivative of that inside? Now I'm doing the product rule. The derivative of e to the x is e to the x, and then I'll leave this one alone. And then now I'll leave e to the x alone, and I'll do the derivative of this, which is that. And now I'm done. That was the very, very inside. So, yeah, I guess I'm actually good. So, I think if I write the dx small, then it'll show up on the scan. If I write too far to the right, then it doesn't show up, but I think this will be fine. And that's it. It's, like I said, all you do is you find the derivative and then you write a dx at the very end. So all of the work was just finding the derivative, and I made sure to give us a nice complicated derivative to make some work for us. But that's where all the work was, is finding the derivative.